Welcome, this is the Sleepy BrainDose, a quiet space where science is told slowly, gently, like a soft rhythm of breath. Tonight, we follow the life of stars, from their first beginnings in dark clouds, through their shining years, to the calm of their final transformations. You may simply listen, let the words drift by, and rest into the flow. You may allow yourself to rest into the thought that the story of every star, no matter how bright or short-lived, begins in stillness. In the vastness of space, there are enormous regions where matter gathers in gentle swirls. These regions are called nebulae, clouds made mostly of hydrogen, the simplest and most abundant element in the universe. Mixed within them is dust, tiny particles of heavier elements, the quiet residue of earlier generations of stars. Together, gas and dust drift slowly, suspended in what feels like endless darkness. There is no rush in this beginning. Everything happens in a rhythm measured not in years, but in millions of years. You can picture the way a breath expands and contracts, and then imagine that same rhythm drawn out across the cosmos. The clouds move with similar patience, carried by gravity, by the faint pull of nearby stars, and by currents of energy spreading through the galaxy. Nebulae are not uniform. Some areas are thin and diffuse, so delicate that a spacecraft could pass through without noticing more than a slight haze. Other areas are thicker, denser, like hidden pockets of material gathering. In silence, within those denser regions, the story of new stars slowly begins. It is a process of concentration, as if the universe is quietly deciding where to kindle its next lights. Gravity is the main actor in this slow dance. Hydrogen atoms are light, but even the faintest mass attracts. Over immense spans of time, small irregularities in the cloud cause matter to clump. Where there is just a little more density, gravity pulls more strongly. Gas drifts inward, dust settles together, and gradually a knot of matter forms. Nothing sudden occurs. It is as if the universe is humming a low, continuous tone, and the particles are moving to its vibration. Astronomers sometimes call these places stellar nurseries. The phrase is simple and soft, because just as a nursery is a place of beginnings and gentle growth, so too are these clouds the safe cradle where stars come into being. Some of the most famous nebulae, like the Orion Nebula or the Eagle Nebula, are vast nurseries where thousands of stars may form together. Yet even in their immensity, the process remains quiet. Gas thickens, temperature slowly rises, and density builds in the heart of the cloud. For a long while, the forming center is still invisible. Light cannot easily escape the surrounding dust, so telescopes that see invisible light record only shadowy regions. But with infrared or radio eyes, astronomers can peer deeper and detect the warmth of the gathering gas. These observations confirm what theory has long described, that every star is born from a hidden core, a place shielded from sight until the fire inside becomes strong enough to pierce the darkness. The chemistry of these clouds adds subtle texture to the story. While hydrogen is by far the most common ingredient, there are also traces of helium and tiny amounts of oxygen, carbon, nitrogen, and more complex molecules. Some regions even contain water vapor, frozen ices, or organic compounds, the very seeds of life. The presence of these elements tells us that stars do not simply create themselves in isolation. They inherit the products of previous stars. In that sense, each new star is part of a continuous cycle, a rhythm in which matter is endlessly reused. Consider how vast these clouds can be. A single nebula might stretch across dozens of light years. If you tried to cross one, even at the speed of light, the journey would take tens of years. And yet, despite their immensity, the density of material inside is extraordinarily low. Imagine spreading a single grain of dust across the space of a living room. That is how sparse most of these clouds are. What gives them weight and significance is their size, not their thickness. Only in their densest knots do they hold enough mass to trigger collapse. That collapse is not violent, but slow and graceful. As the gas contracts under gravity, it releases energy. Atoms move faster, heat builds, and the central region becomes warmer. The balance of pressure and pull keeps shifting, drawing more material inward. The process may take millions of years. If you were able to watch it unfold in real time, you would see almost nothing change. Yet on the scale of cosmic history, it is the steady pulse that leads to birth. The darkness of these clouds can be imagined as a kind of protective softness. In visible light, they often appear as dark patches against the brighter background of stars. Astronomers call them dark nebulae, places where dust blocks the light behind. But within that obscurity, hidden from sight, creation is happening. The darkness is not an absence. It is a womb, sheltering fragile beginnings until they are strong enough to shine. Some of the most well-known regions of star formation show striking shapes, carved by the gentle action of radiation and stellar winds from nearby young stars. The pillars of creation in the Eagle Nebula, for instance, are towering columns of gas, eroded into form by light. Yet even these dramatic structures change only slowly, over thousands of years. Their beauty lies not in sudden movement, but in patient transformation. When astronomers map these clouds, they notice patterns. Star formation is not random, but tends to happen in clusters. Dozens or hundreds of stars may arise close together, sharing a common birthplace. Later, gravity and galactic tides may disperse them, but their shared origin can sometimes be traced in the chemical fingerprints they carry. The atoms in their atmospheres, the subtle ratios of elements, reveal the cloud that gave them life. It is a reminder that even stars, which seem solitary in the night sky, often begin as part of a quiet community. The clouds also tell us about the rhythm of galaxies. In the spiral arms of galaxies like our Milky Way, waves of density move through the disk, compressing gas and sparking star formation. Where the arms pass, nebulae glow and young stars appear. Then the wave moves on, leaving behind clusters of shining newborns. This pattern repeats endlessly, a cosmic heartbeat driving the cycle of birth dot in the soft perspective of calm science. What matters is not the precise equations or the technical detail, but the gentle awareness that the universe holds these nurseries everywhere. They are not rare. They are scattered across our galaxy and across billions of galaxies beyond. Each one is a quiet room of beginnings, a place where the darkness is filled with potential. The life of stars begins not with explosion, but with stillness. Not with sudden light, but with the long patience of gas gathering into knots. You may notice how that rhythm reflects your own breathing. The slow intake, the pause, the release. In the same way, the universe breathes stars into being. From clouds of gas and dust, through the soft pressure of gravity, the seeds are set. And in their time, they will grow into light. It is enough, for now, to rest with this knowledge, that the stars you see in the night sky once rested too, hidden in darkness, waiting quietly to begin. Every star spends much of its earliest life hidden. It does not appear suddenly, shining in brilliance, but grows slowly inside a cocoon of gas and dust. What astronomers call a protostar is not yet a true star, because the central fire of nuclear fusion has not fully begun. Instead, it is an object in transition, shaped by gravity, warmed by contraction, and wrapped in the shelter of its parent cloud. Understanding this stage allows us to see how the first glimmers of light emerge in the universe, not as sudden flashes, but as a gradual awakening. The story begins in the dense regions of a molecular cloud. These are places where hydrogen molecules, helium, and fine grains of dust collect more thickly than in their surroundings. Under the slow but constant pull of gravity, material drifts inward, piling into a central region. As the mass increases, gravity grows stronger, drawing in even more gas. This process is self-reinforcing, yet always gentle on the timescale of millions of years. From afar, nothing seems to change. Within the cloud, however, pressure and heat rise quietly, like breath accumulating in the chest before it is released. At the heart of the collapsing knot, atoms are pressed closer together. Motion increases, collisions become frequent, and the temperature rises to thousands of degrees. The heating is not caused by nuclear fire, but by the release of gravitational energy. When gas falls inward, it loses potential energy, and that energy becomes heat. This warming core is what astronomers identify as a protostar. It is not yet stable, not yet balanced, but already something more than the diffuse gas around it. For a long time, the protostar remains invisible to human eyes. Thick envelopes of dust absorb visible light and re-emit it in infrared, which is why infrared telescopes are crucial for observing star birth. When astronomers look into regions such as the Orion Nebula, they detect tiny warm spots glowing in wavelengths beyond human sight. Each of these is a young protostar wrapped in its shroud, waiting for the next step. This hidden nature gives the protostar stage a special character. It is a time of gestation, sheltered and quiet, not yet ready to emerge into full radiance. Around many protostars, disks of material form naturally. As gas falls inward, even a slight rotation is amplified. Conservation of angular momentum ensures that matter cannot collapse directly to the center, but instead flattens into a rotating disk. These disks are not merely side effects. They are the birthplaces of planets, comets, and smaller bodies. Long before a star reaches maturity, the seeds of planetary systems are already present, circling in silence. It is a reminder that the life of stars and the life of worlds are intertwined from the very beginning. The protostar itself changes slowly. As more mass accumulates, gravity compresses the center further. The core temperature climbs steadily, from thousands to tens of thousands of degrees. The surrounding envelope becomes thinner as stellar winds begin to push material outward. Eventually, outflows of gas stream along the star's poles, clearing away some of the cocoon. These outflows are not violent in our sense of time. They unfold across tens of thousands of years. But they sculpt the cloud, leaving behind cavities and filaments that later shine in reflected starlight. During this stage, the balance between inward pull and outward pressure is not yet complete. The protostar may brighten and dim, shift in size, or shed part of its envelope. These fluctuations are not chaos, but the natural rhythm of settling into stability. Each adjustment brings the star closer to equilibrium. You may think of it as the gentle rocking of a cradle, where movement is part of finding rest. When the core temperature approaches several million degrees, the conditions for nuclear fusion begin to emerge. At first, only a trickle of fusion occurs, not enough to halt collapse completely. The protostar continues contracting, but fusion gradually strengthens. The journey is one of balance seeking, like two forces slowly learning to share the same rhythm. Eventually, when hydrogen fusion in the core generates sufficient outward pressure to counter gravity, the star has reached the main sequence. But Before that point, it is still called a protostar, an in-between stage, filled with potential. Astronomers sometimes classify these stages with technical terms, Class 0, Class I, and beyond, depending on how much material surrounds the star and how visible it is in different wavelengths. Yet beneath the labels lies a simple picture. Clouds condense, centers warm, disks form, outflows shape the surroundings. Each stage is a step in a continuous process, not abrupt, but smooth. The scientific detail is fascinating, but what matters here is the awareness of the universe's patience. A star spends millions of years in this hidden phase, preparing quietly for the long journey ahead. Protostars also remind us that beginnings are not perfect. Many condensations fail to gather enough mass to ignite sustained fusion. Some become brown dwarfs too small to shine as stars, glowing only faintly from residual heat. Others may dissipate before stabilizing. But even these outcomes are part of the cosmic rhythm, redistributing matter, ensuring that nothing is wasted. The universe allows many attempts, and from them, some stars succeed. Looking at star-forming regions in detail, astronomers see clusters of protostars, often at different stages of growth. It is as if one could walk through a forest and see seeds, sprouts, young trees, and mature giants side by side. In the calm view, this reveals that stellar birth is not isolated but collective. Clouds give rise to families of stars, some destined to shine brightly, others quietly fading, all contributing to the balance of the galaxy. In the context of cosmic history, protostars are fragile but essential. They are the transition between raw material and enduring light. Without them, galaxies would be only clouds of gas, dark and cold. With them, the universe gains warmth, structure, and the foundation for everything that follows: planets, chemistry, and eventually life. It is worth resting on the thought that the atoms in our bodies were once part of similar clouds, gathered slowly, warmed gently, and eventually lit by the first sparks of fusion. The stage of the protostar is not about brilliance or spectacle. It is about preparation, about the quiet persistence that leads to stability. You may notice the similarity to your own breathing, to the way rest prepares the body for activity. The universe, too, rests its stars before they shine. In the darkness of their cocoons, they gather strength, shaping disks, sending out soft flows, adjusting to the rhythm of gravity and heat. When you look at the night sky and see a bright star, remember that its light was once hidden, wrapped in silence for millions of years. The protostar stage is a reminder that even in the cosmos, growth requires time, shelter, and gradual unfolding. Nothing rushes. Nothing forces its way forward. The universe teaches patience through the lives of its stars. And so, the first light is not a sudden blaze, but a slow glow building in the heart of a cloud. It begins faintly, shielded from view, nurtured by gravity's embrace. Over time, it strengthens, steadies, and prepares to step into the main sequence. Until then, it is a protostar, an object not fully one thing or another, but quietly becoming. In this calm transition lies the beauty of beginnings, where potential and patience meet. In the center of every true star lies a process both simple and profound. It is called nuclear fusion, and though the name may sound technical, at its heart it is nothing more than atoms combining. In the dense, hot interiors of stars, hydrogen, the smallest and most abundant element in the universe, merges into helium. From that quiet transformation flows light, heat, and the stability that allows a star to shine steadily for millions or even billions of years. The road to fusion begins once the protostar stage has brought the core to sufficient temperature and pressure Imagine the way heat slowly rises in a hearth until wood finally catches and burns steadily. In a similar way, gravitational contraction raises the core temperature of a forming star. When that temperature reaches around 10 million degrees, the motions of hydrogen nuclei become so energetic that they can overcome their natural tendency to repel one another. At that point, fusion begins. Hydrogen atoms consist of single protons, and protons carry positive charge. Under ordinary conditions, these charges repel each other strongly. If you bring two hydrogen nuclei close together on Earth, they simply push apart. But in the compressed, overheated heart of a star, the rules bend. The protons move with enormous speed. Occasionally, two come close enough that a different force takes over the strong nuclear force, which binds particles together once they are within a tiny distance. The moment this happens, the protons fuse and a new particle is formed. Process is not instantaneous or explosive, but ongoing and balanced. One proton may convert into a neutron through a rare transformation, releasing a small particle and energy. Then, step by step, the nuclei combine to form helium. Along the way, light particles called photons and ghostly neutrinos are released. The photons scatter, bounce, and gradually make their way outward. This is the light that, much later, after traveling through layers of plasma and across space, reaches us as the glow of the stars we see at night. What is remarkable is not just that fusion produces energy, but that it does so with extraordinary steadiness. Each individual reaction is tiny, releasing far less energy than the burning of even a single grain of sand. But in the dense core, reactions happen endlessly, with countless trillions occurring every second. Together, they add up to a continuous flow of power. For the Sun, the amount is vast. Every second, it converts about 600 million tons of hydrogen into helium, releasing energy that radiates in all directions. Yet despite such numbers, the process is so balanced that the Sun remains stable for billions of years. The stability arises from the interplay between gravity and fusion. Gravity always tries to compress the star, pulling its mass inward. Fusion, by producing heat and radiation, pushes outward. The two forces meet in equilibrium, like two hands pressed gently against each other, equal in strength, neither overwhelming the other. This balance is why stars can exist in the main sequence stage for such immense lengths of time. It is a quiet tension, a harmony that sustains their light. In smaller stars, the process runs slowly. Their cores are less hot, their pressures lower, so fusion proceeds at a gentle pace. That gentleness means longevity. A red dwarf star may shine for trillions of years, far longer than the current age of the universe. Larger stars, by contrast, burn quickly. Their greater mass creates higher core temperatures, which drives fusion more intensely. These stars exhaust their fuel in only millions of years, brief on cosmic scales. Whether slow or fast, however, the principle remains the same. Fusion is the quiet fire that defines a star's being. Astronomers describe different pathways of fusion. In stars the size of the Sun or smaller, the main process is called the proton-proton chain, where hydrogen nuclei gradually link to form helium. In more massive stars, another cycle, known as the CNO cycle, dominates, where carbon, nitrogen, and oxygen act as catalysts to speed the fusion of hydrogen. The names and details can seem complex, but the underlying truth is simple. Hydrogen becomes helium, and energy is released. This energy is what sustains the star and allows it to radiate light across space, not from our calm perspective. It is worth noticing the scale of time involved. Once fusion begins, It continues for billions of years in stars like the Sun, throughout all of human history. And long before it, the Sun has been powered by the same steady reactions. It will continue far into the future, its output varying only slightly as it ages. The constancy of this process has made life on Earth possible, because without a stable source of energy, our planet would not have warmth, light, or the cycles that sustain ecosystems. Deep in the core, the photons created by fusion do not travel directly outward. They scatter in endless zigzags, absorbed and re-emitted by particles of plasma. A photon that originates in the Sun's core may take hundreds of thousands of years to reach the surface. By the time it emerges, it is just one of countless streams of light blending into the glow we see. The journey of each photon is long, but the effect is smooth. The Sun shines evenly, without flicker, because the process averages out over unimaginable numbers of reactions. Fusion also forges the first step in cosmic alchemy. Hydrogen, the simplest element, is transformed into helium, the second element. In later stages of stellar evolution, fusion will create heavier atoms, building the periodic table element by element. But it begins with hydrogen and helium, the foundation of stars. The very act of fusion is the universe's way of generating complexity, starting from simplicity and moving toward diversity. You may notice how this mirrors natural patterns we know on Earth. Life too begins from simple beginnings, cells dividing, structures building, each stage sustained by a flow of energy. In the same way, stars build themselves through fusion, small changes repeated countless times until stability emerges. The rhythm is the same, slow, patient, enduring. Although fusion in stars is immensely powerful, the feeling it gives is not one of violence, but of security. For billions of years, the Sun's fusion has created a steady environment in which Earth can orbit peacefully. The heat that warms your skin on a summer's day began as fusion reactions deep inside the solar core, reactions that may have occurred before the first humans walked the Earth. The warmth is ancient, and yet it continues, a constant offering of energy. When you look at the stars on a quiet night, you are seeing the outward sign of this inner fire. Each point of light is a beacon powered by fusion. You are looking at the balance between gravity and energy, at hydrogen transformed into helium, at the quiet pulse of the cosmos. It is easy to forget how patient and stable the process is, because the stars appear so timeless. But it is this very patience, the slow persistence of fusion, that allows stars to seem eternal in human eyes. Resting with this thought can be soothing. There is no urgency in fusion. It unfolds naturally, maintaining balance for eons. Stars are not rushing toward their end. They are breathing in the rhythm of fusion, exhaling light, inhaling gravity, and holding steady in between. The fire within them is not a blaze, but a calm heartbeat, a flow that sustains the universe gently and continuously. And so nuclear fusion, though it sounds complex, is simply the merging of the simplest atoms, producing light that travels across the darkness. It is the quiet inner fire, invisible yet essential, giving each star its presence. Every star you see in the sky is living through this process now, holding its balance, shining because hydrogen and helium are in endless conversation at its core. To know this is to feel the deep steadiness of the universe, where even fire is calm and even power is gentle. Once a star has kindled its inner fire through fusion, it enters a stage of life that is both enduring and tranquil. Astronomers call this phase the main sequence. It is the time when hydrogen fusion in the core produces just enough energy to counteract the inward pull of gravity. The star does not collapse further, nor does it swell uncontrollably. Instead, it finds a quiet equilibrium, a balance that can last for millions, billions, or even trillions of years, depending on the stars. Mass. For the vast majority of its life, a star remains in this state of calm continuity. The Sun, which provides light and warmth to our planet, has been in its main sequence for more than 4 billion years. It will remain there for another 5 billion. Throughout all of human history, and long before life even appeared on Earth, the Sun has held this balance. Day after day, century after century, it has shone with nearly unchanging brightness. This constancy is why life on Earth could develop. Without it, climates would not stabilize, seasons would not repeat, and ecosystems could not flourish. A main sequence is, in many ways, the universe's gift of stability. What defines this phase is the perfect counterpoint between two great forces. Gravity presses inward, trying to contract the star. Fusion presses outward, creating heat and radiation that push against collapse. At the main sequence, these forces are equal. The star's size, temperature, and brightness may shift slowly over time, but on human scales, they are constant. If you were to observe a star in this stage, over the course of thousands of years, you would notice almost no change. It is like watching a calm lake whose surface ripples gently but never loses its form. The main sequence includes stars of many sizes and colors. Small stars, called red dwarfs, glow faintly with cool light. They burn their hydrogen slowly and can remain on the main sequence for trillions of years, longer than the current age of the universe. Medium stars, like the Sun, shine steadily for billions of years, with a soft yellow light. Large stars, bright blue giants, blaze intensely, burning their fuel rapidly and lasting only a few million years. Each follows the same principle of balance, though the timescales differ. In all of these cases, the core is where the essential work is done. Hydrogen is continuously fused into helium. The energy produced flows outward, keeping the star stable. The outer layers are heated and emit light into space. This light spreads in all directions, crossing immense distances, eventually reaching other stars, planets, and, in the case of our Sun, Earth itself. The rhythm of fusion inside and radiation outside is so well matched that the star endures. Over time, the chemistry of the core slowly shifts. As hydrogen fuses into helium, the helium builds up. Helium does not fuse at main sequence temperatures, so it accumulates, creating a growing core of inert material surrounded by hydrogen still. Burning. This gradual change is invisible to outside observers, but it is the slow clock that measures the star's time in the main sequence. Eventually, when enough hydrogen is gone, the balance will tip, and the star will leave this stage. But until then, it remains steady got from Earth. The stars we see in the night sky are almost all main sequence stars. Their constancy is why constellations remain recognizable across centuries. Their light has traveled for years or decades to reach us, but it is light from stars living in their most stable state. If you have ever gazed at Orion or the Big Dipper, you have looked at stars in their long middle age, shining reliably in the quiet of the galaxy. The main sequence also reveals the relationship between mass and destiny. A star's mass determines how long it will remain in this phase. The smallest stars sip their hydrogen so slowly that they may never leave the main sequence before the universe itself changes beyond recognition. Larger stars burn brightly, but briefly, using their fuel extravagantly and moving quickly toward later stages. Yet whether slow or fast, Every star passes through this calm middle chapter, where the energy within perfectly matches the pull of gravity without. This idea of balance has a soothing quality. You might think of it as the star's long breath. During the main sequence, the star inhales gravity and exhales fusion, the two motions equal, creating a steady rhythm. Nothing is forced, nothing is rushed. The star is simply being what it is meant to be, existing in harmony with its own nature. That harmony is what allows light to flow across the galaxy, filling the dark with points of brightness. For the sun, this balance has given Earth 4 billion years of continuous energy. Every plant that has grown, every ocean current that has flowed, every breath of air taken by living creatures has depended on the sun's main sequence stability. Even now, as you read or listen, photons born in the solar core hundreds of thousands of years ago are reaching Earth's atmosphere, warming your surroundings in a way that feels ordinary, but is, in truth, extraordinary. If you step back in your thoughts and imagine the galaxy, you might see countless stars, all in their main sequence stages, each one a steady point of light. Together, they form the glow of the Milky Way, a ribbon of stars across the night sky. Each light is a story of balance, of hydrogen quietly transforming into helium, of gravity and fusion in perfect partnership. It is not chaos, but order, not haste, but patience. Astronomers often plot stars on a diagram called the Hertzsprung-Russell diagram, where the main sequence appears as a long band stretching across. Almost every star spends its life there. The diagram is a scientific tool, but in a softer sense, it is like a portrait of the universe's calm. It shows that most stars, most of the time, exist in this steady state. They do not flicker out quickly. They do not rush. They hold their place, shining reliably, like lanterns along a quiet road. The main sequence reminds us that much of the cosmos is not violent, but serene. While the later stages of a star's life may bring change and transformation, the majority of its story is told here, in this long season of balance. It is during this phase that stars provide light for worlds, nurture planets, and make possible the environments where life might arise. The calm of the main sequence is the foundation upon which the drama of the universe rests. To reflect on. This is to recognize the depth of time. Human lives are brief compared to the span of a star's main sequence. Civilizations rise and fall, species come and go, continents drift, yet the stars overhead remain almost unchanged. Their constancy has guided travelers, inspired myths, and given perspective. Even as everything on Earth shifts, the stars remind us of continuity, of patience, of the enduring rhythm of the universe. And so, when you see the night sky, you are witnessing the main sequence in action. You are seeing stars in the middle of their journey, balanced between gravity and fusion, shining quietly across the ages. Their light carries with it the message of steadiness, that the universe is not only about change and endings, but also about long stretches of harmony. Stars teach us that balance can last, that calm can endure, that the inner fire can be both powerful and gentle. When a star settles into the main sequence, it may seem to have found a universal pattern of balance. Every star, no matter how distant, shines because fusion in its core balances the inward pull of gravity. Yet beneath this shared rhythm lies a quiet difference, determined from the very beginning. The mass of a star, the total amount of matter it gathers during its birth, decides how it will live, how it will shine, and how it will eventually fade. In the stillness of cosmic time, mass is the gentle hand that guides destiny. Small stars, modest in their size, follow one path. Large stars, immense in their weight, follow another. Both breathe through fusion. Both rest in the calm of equilibrium, yet the pace of their lives diverges. A small star burns fuel slowly, like a candle with a tiny flame. A massive star blazes, furiously, consuming its hydrogen at an astonishing rate. The contrast is not dramatic in appearance when we look at the night sky, for both appear simply as points of light. But in the life of the star itself, the difference is profound, not red. Dwarfs are the smallest stars capable of sustaining hydrogen fusion. Many of them are less than half the mass of the Sun, some only a tenth. Their surfaces are cool compared to larger stars, glowing with a soft, faint red. Because they are so small, their gravity presses less strongly on their cores. Fusion proceeds, gently, releasing energy slowly. As a result, red dwarfs live extraordinarily long lives. Some may shine for trillions of years longer than the universe itself has yet existed. Even now, none of the red dwarfs that formed in the earliest days of the cosmos have had time to die. They are still shining quietly, their endurance unmatched. By contrast, the largest stars, with masses tens of times greater than the Sun, live with intensity. Their immense gravity crushes their cores to temperatures far hotter than those of smaller stars. Fusion races ahead at a furious pace, consuming hydrogen rapidly. These stars shine with blinding blue-white light, visible across great distances, but their brilliance is fleeting. In only a few million years, a blink on cosmic scales, they exhaust their hydrogen and move swiftly into later stages. For them, life is short but radiant. Between these extremes lie stars like our Sun, with medium mass and lifespan. They live for billions of years, neither as eternal as red dwarfs, nor as brief as blue giants. Their light is steady, their rhythm balanced. They remind us that mass does not dictate value, but simply sets the tempo of existence. Each kind of star, whether faint or brilliant, contributes to the cosmic symphony in its own way. The differences in mass also shape how stars end their lives. Small stars, burning gently, will eventually cool into white dwarfs, fading slowly into darkness. Large stars, burning fiercely, will end in supernova, leaving behind neutron stars or black holes. The seeds of these endings are sown in the mass at birth. A small star never has the weight to ignite the fusion of heavy elements, while a massive star races through each stage of fusion until collapse becomes inevitable. Destiny unfolds not with drama, but with quiet inevitability. It is helpful to think of mass as the quiet clock within each star. From the moment of its birth, the amount of material gathered sets the pace of fusion, the length of the main sequence, and the final form it will take. The star does not choose, nor does it resist. It simply follows the path laid out by its mass, moving patiently through its life stages. This awareness can be soothing. The universe itself accepts difference, allowing some stars to live long and faint lives, others to live short and bright ones. Without judgment or comparison. From our vantage point on Earth, the night sky holds both kinds. The faint red dwarfs are too dim to be seen without telescopes, but they make up the majority of stars in the galaxy. They are the quiet background, the unseen hosts of countless planets. The brighter stars that catch our eye, the blue giants. In Orion, the luminous beacons in constellations are the massive ones, rare but striking. The sky is therefore a blend of hidden endurance and visible brilliance, shaped entirely by the difference in stellar mass. In reflecting on this, one can notice parallels with rhythms closer to home. Some lives move slowly, with patience, stretching across long spans of time. Others move quickly, shining brightly, leaving a mark in a shorter period. Both paths are natural, both meaningful, each one part of the larger flow. The stars remind us that variety is not disorder, but part of balance. Scientists use the phrase stellar evolution to describe how stars change over time. It might sound like a process of progress, but in truth, it is a cycle guided by mass. Small stars evolve by lasting. Large stars evolve by burning fast and transforming into new states. Each outcome contributes to the galaxy. Red dwarfs provide stability for trillions of years. Massive stars enrich space with heavy elements when they end, seeding the material for new stars and planets. Nothing is wasted. The paths are different, but together they form the whole dot. It is worth pausing on the idea that the faintest stars outnumber the brightest by far. Red dwarfs may not dominate the sky visually, but they dominate in number. Our galaxy is filled with them, unseen companions scattered in every direction. If you could see them all at once, the sky would be thick with points of soft red light. This hidden abundance speaks of quiet strength, of endurance beyond measure. At the same time, the rare massive stars, though few, shape their surroundings powerfully. Their intense radiation sculpts nearby clouds. Their short lives end in supernovae that distribute elements across space. In their brief time, they have influence far beyond their numbers. The galaxy needs both, the quiet majority and the brilliant minority, each serving a role in the cosmic order. And so, the paths of stars begin to differ once they enter the main sequence. Small stars lean toward longevity, large stars toward intensity. Each path is written in the mass gathered at birth, a silent decision made by the universe itself. When you look at the sky, you are seeing both stories at once, the unseen endurance of the many and the visible brilliance of the few. Together, they weave the tapestry of starlight, patient and varied, yet unified in balance. At the heart of every star lies a conversation between forces. One is gravity, the universal attraction that pulls all matter together. The other is pressure, born from the heat and energy of fusion reactions in the core, pushing outward. If gravity were alone, a star would collapse endlessly, shrinking into a denser and denser state. If pressure alone had its way, the star would expand without limit, scattering its material into space. But when the two meet in balance, a star takes form and holds steady. This delicate equilibrium defines almost every stage of stellar life. And it is the quiet reason why stars can shine calmly for so long. Gravity, though invisible, is relentless. From the moment a cloud of gas begins to collapse into a protostar, gravity is the hand guiding the process. It draws atoms inward, concentrates material, and raises the pressure at the center. Without gravity, the gas would remain diffuse forever. But gravity has no intention of stopping on its own. Left unchecked, it would compress matter endlessly until atoms themselves could no longer resist. What halts this process is the energy released inside the star. That energy comes from fusion, the merging of hydrogen nuclei into helium deep in the core. Fusion produces not only light, but also heat. Heat, in physical terms, is motion particles moving rapidly, pressing against one another. This motion creates pressure, which pushes outward. In a star, the pressure from the hot core radiates through the layers, balancing the weight of the star's mass, pressing inward. The balance point is not fragile in the sense of being unstable, but precise. It can last for billions of years. A calm agreement between two opposing tendencies. In physics, this equilibrium has a name: hydrostatic balance. The word sounds technical, but the idea is simple. At each layer within a star, the inward pull of the material above is exactly matched by the outward pressure from below. No part of the star is left unbalanced. From the outer atmosphere down to the central core, the two forces meet in harmony. This is why a star can maintain its shape, neither shrinking nor swelling uncontrollably. The star is, in essence, breathing in and out at once, the motions held in a quiet stillness. The role of balance becomes clearer when we think of what happens if it shifts. If gravity gains the upper hand, the star contracts. As it contracts, the core heats further because compressing matter raises its temperature. The higher temperature speeds up fusion, which increases pressure. Pressure then pushes back against gravity, restoring balance. If pressure becomes too strong, the star expands. As it expands, the core cools slightly, slowing fusion, reducing pressure, and again returning to equilibrium. In this way, stars naturally stabilize themselves. Their balance is self-correcting, a built-in rhythm of adjustment that keeps them steady. For the Sun, this equilibrium has lasted for billions of years. Gravity has pulled relentlessly on its mass, but fusion has provided equal resistance. The surface we see, the photosphere, is the visible expression of that balance. Every ray of sunlight, every photon warming Earth, is part of the exchange between inward pull and outward push. Without it, the Sun would not exist as we know it. It would either collapse into a smaller, denser object or disperse into space. Instead, it rests in the calm of hydrostatic balance, shining steadily. The concept of balance also applies to stars of different sizes. In small stars, the inward pull of gravity is weaker, and so the required pressure from fusion is gentler. This makes their lives longer as they sip fuel slowly. In massive stars, gravity presses with enormous strength. To balance it, fusion must proceed furiously, generating immense outward pressure. This speeds up their lives, forcing them to burn brightly but briefly. In both cases, it is the same balance, adjusted to match the star's mass. The universe applies no single rule, but a principle that scales to each circumstance, keeping harmony across differences. One can also see balance in the way stars interact with their surroundings. The pressure of starlight and stellar winds flows outward, shaping nearby clouds. Gravity, meanwhile, draws in material during formation, gathering mass. The same two forces that govern a star's interior also shape the galaxy at large. Balance is not confined to the star itself, but is woven into the broader structure of the cosmos. The language of gravity and pressure may sound abstract, but the underlying picture is simple. Stars survive because two forces meet in the middle. Neither wins, neither loses. They sustain each other by holding each other in check. In a sense, gravity gives the star its body, while pressure gives it its breath. Without one, the other would run away. Together, they create stability. It is soothing to realize that what seems like eternal starlight is the result of constant, subtle negotiation. The forces are immense, but their interaction is smooth. Stars do not tremble on the verge of collapse. Every moment, they rest securely within the balance, adjusting only gradually as their cores evolve. This is why stars, when observed over human timescales, seem unchanging. The night sky appears eternal because the forces within stars are balanced, so precisely that change is measured only in millions of years, as a star ages. The balance does shift because the fuel in the core is slowly consumed. When hydrogen decreases, fusion weakens. Gravity then begins to compress the core again, raising temperatures until new forms of fusion can occur. The process leads to later stages in a star's life, when it swells into a red giant, or, for massive stars, races through heavier elements. Yet even then, the principle of balance persists. At each stage, gravity presses, fusion resists, and the star finds a new point of equilibrium. However temporary, this gentle rhythm, gravity inward, pressure outward, is one of the most fundamental patterns in the universe. It is present not only in stars, but in planets, in galaxies, even in the structure of space itself. Yet stars give us the clearest example, because their balance shines visibly across the night sky. To see a star is to see balance in action, a quiet harmony between forces that might otherwise seem opposed. If you allow yourself to rest with this thought, it can feel like a reflection of balance in life. Forces pull us inward, others push. Use outward. Stability comes not from eliminating one, but from allowing them to meet. Stars remind us that balance is not stillness in the sense of absence, but a living, dynamic state. Within them, billions of reactions happen every second. Gravity never ceases, pressure never pauses. Yet the whole is calm, held in harmony. So, the role of gravity in balance is not only technical, not only physical. It is the quiet foundation of existence for every star you see. It is the reason the sun has shone for so long, the reason constellations endure, the reason galaxies glow. When you look at the night sky, you are witnessing equilibrium across unimaginable distances and times. It is a balance so precise that stars can live for billions of years, yet so natural that it requires no effort. The universe holds its harmony gently, and in that harmony, stars shine. When a star has spent long ages in the calm rhythm of the main sequence, quietly fusing hydrogen into helium, the balance eventually begins to shift. The hydrogen in its core is not infinite. Over billions of years, more and more of it is transformed into helium, and the store of fuel slowly diminishes. The star does not falter suddenly, but the change begins quietly, deep within, where the eye cannot see. The fusion that has held gravity at bay weakens, and gravity, as always, begins to press inward once more. This is the moment that leads to the transformation into a red giant. A new stage in the star's journey got as the hydrogen supply in the core thins, fusion there fades. Gravity then compresses the helium-rich center, and compression means heating. The temperature rises until hydrogen outside the core, in a surrounding shell, becomes hot enough to ignite. Fusion begins again, not at the very center, but in this narrow shell around the helium core. The effect is subtle at first, but the consequences are immense. The shell burning produces more energy than the star can radiate steadily, and that surplus energy pushes outward, swelling the outer layers of the star. What follows is expansion on an enormous scale. The star's outer atmosphere stretches outward, sometimes to hundreds of times its original size. If our sun were to expand to red giant dimensions, its outer edge would extend beyond the orbit of Mercury, perhaps even engulfing Venus. The expansion is not violent, but gradual, unfolding over millions of years. From the outside, the star appears much larger, its surface cooler, its light shifting toward a soft red. It is from this change in color that we call them red giants. The cooling of the surface is a natural result of expansion. As the outer layers spread over a larger area, their energy is diluted. The temperature drops to only a few thousand degrees, far cooler than the sun's present surface. This is why red giants shine with a ruddy glow, gentle and subdued, compared to the hot blue-white of massive young stars. Their light is not weaker in total indeed. Red giants often shine with greater overall luminosity because of their huge size, but it is softer in color, spread across a vast surface. Inside, the helium core grows denser and hotter. For stars like the sun, this core remains inert for a time, unable to fuse because the temperature is not yet high enough. It contracts under gravity, becoming more compact, while the shell around it continues to fuse hydrogen energetically. In more massive stars, the helium core can eventually ignite, fusing helium into carbon and oxygen. But for now, in the early red giant phase, the defining feature is the burning shell and the swelling outer layers. From the perspective of observation, red giants are among the most striking stars in the sky. Betelgeuse in Orion, Aldebaran in Taurus, and Arcturus in Boats are well-known examples. These stars appear distinctly orange or red to the naked eye, their glow softer and more diffuse than that of smaller, hotter stars. They remind us that stars change across time, and that even familiar constellations carry within them stars at different life stages. The process of becoming a red giant is, like all stellar evolution, governed by balance. Gravity squeezes inward, fusion in the shell pushes outward, and the star expands until the two forces once again find harmony. The star does not break apart or collapse instantly. Instead, it discovers a new equilibrium, one defined by a swollen body and a cooler face. It may remain in this state for hundreds of millions of years, depending on its mass, continuing to shine steadily in its altered form. The change from main sequence to red giant is also a change in structure. The outer layers of the star become more diffuse, less tightly bound to the core. The atmosphere can stretch so far that it is only tenuously held by gravity. This is why red giants often lose material into space, creating stellar winds that drift outward, enriching their surroundings with gas and dust. These outflows are not storms, but soft exhalations, part of the natural rhythm of the star as it ages. For a star like the Sun, the red giant stage will be a profound transformation. After billions of years of steady yellow light, it will expand, becoming thousands of times brighter, though cooler on its surface. Earth by then may no longer be habitable, but the Sun itself will remain a star, finding a new form of balance. It is a reminder that stars, like all things, change with time, yet their changes are part of a continuous cycle, not a sudden break. The sight of a red giant conveys a sense of age and maturity. These stars are not young, rushing through their fuel, nor are they remnants fading into silence. They are in a middle stage, transformed, but still vigorous, radiating with immense power softened by cool surfaces. Their presence in the sky has inspired myths and stories across cultures, for their red glow stands out clearly. Yet beneath the appearance lies the same physics as always. Gravity and fusion and delicate conversation dot in the calm view. The red giant phase is simply the next breath in the life of a star. Expansion is not an ending, but a shift, a natural response to the exhaustion of core hydrogen. Cooling is not decline, but adaptation, the surface spreading out while the inner fire rearranges itself. The star is not failing, but evolving, carrying its light forward in a new form dot as you imagine these vast suns swelling and glowing softly red. You may notice the rhythm they share with the universe itself. Just as your breath expands and releases, so too does a star expand when its inner fuel shifts. Just as balance is found anew in each moment, so too do stars find new equilibria as they age. The red giant phase is therefore not a crisis, but a renewal, another way in which the cosmos shows its patience and continuity. And so, a red giant is not merely a large star. It is a symbol of transition, of endurance through change, of light continuing in altered form. It reminds us that even in transformation, there is beauty and calm. The universe, through its stars, teaches that growth and change need not be violent. They can be as gentle as a shift in color, as soft as the glow of red light spreading across the night. As stars like our sun near the end of their long journeys, they undergo a transformation that is both subtle and beautiful. After spending billions of years on the main sequence, and then swelling into red giants, their fuel supply dwindles further. Hydrogen has long since burned in the core. Helium has been fused into heavier elements such as carbon and oxygen, and now the central fire begins to fade. These stars cannot reach the immense pressures and temperatures required to fuse much beyond helium. Instead, they approach the close of their lives with a final act of release, a gentle shedding of their outer layers, creating what astronomers call a planetary nebula dot. The name is misleading. These objects have nothing to do with planets. Early astronomers, viewing them through small telescopes, thought they resembled disks like those of distant worlds, and the term remained. In truth, a planetary nebula is the soft halo of gas expelled by a dying star, illuminated by the light of the hot core left behind. Rather than fading quietly into invisibility, these stars exhale their atmospheres into space, creating luminous shells that can glow for tens of thousands of years. The process begins when the red giant can no longer maintain balance. The helium in the core is exhausted, and fusion dwindles. Gravity presses inward again, and the core contracts further, heating to extraordinary levels. But in the outer layers, the story is different. Those layers are tenuously bound, swollen. By the earlier giant phase, the pressure from below pushes them outward, and the star's weak grip allows them to drift away. In stages, sometimes in pulses, the outer layers detach and flow into surrounding space. What remains is a striking contrast: a dense, hot core surrounded by an expanding cloud of gas. The core, now exposed, shines intensely in ultraviolet light. That radiation streams outward, striking the drifting shells of gas. Atoms in the gas absorb the energy and re-emit it as visible light. The result is a glowing nebula, delicate in form, shining with colors that depend on the elements present. Hydrogen glows red, oxygen emits green or blue, nitrogen adds subtle shades. Together, they create patterns of soft light across the darkness. Through telescopes, planetary nebulae appear in many shapes. Some are nearly spherical, gentle halos expanding evenly. Others are elliptical or shaped into rings, or even more. Complex forms, sculpted by the influence of stellar winds, magnetic fields, or companion stars. Famous examples include the Ring Nebula in Lyra and the Helix Nebula in Aquarius. They look like cosmic flowers, fragile and symmetrical, their forms expanding quietly into the night. Each is a final signature of a star like the Sun, recorded in glowing gas. For the star itself, the shedding of layers is not an ending of energy, but a shift in balance. The core, stripped of its outer shells, becomes a white dwarf, small, dense, and hot, but no longer sustaining fusion. The white dwarf shines for billions of years as it slowly cools, while the nebula surrounding it expands and disperses. In time, the glowing shell fades, merging with the interstellar medium, the vast reservoir of gas and dust that fills the galaxy. Nothing is lost. The atoms that were once part of a star's atmosphere drift outward, joining the material that will form new stars, planets, and perhaps, in time, living beings. This recycling of matter is one of the most profound truths revealed by planetary nebulae. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all were forged in stars and released through processes like these. Without the quiet exhalations of dying stars, the universe would remain simple, composed mostly of hydrogen and helium. It is through such final breaths that the cosmos gains richness, variety, and the elements that make life possible. From Earth, we can see only the luminous beauty of these nebulae, but their deeper meaning lies in their role. In the cosmic cycle, they are reminders that endings are not simply closures, but beginnings for something else. A planetary nebula is both the conclusion of one star's journey and the preparation for countless new ones. The gas drifts outward, cools, and becomes part of the interstellar clouds where new stars will be born. In this sense, every planetary nebula is a bridge between generations of stars, in the calm perspective. This stage of a star's life can be imagined as a gentle exhalation. The star, having burned steadily for billions of years, finally lets go of what it no longer needs. Its outer layers flow into the surrounding space, not in violence, but in soft release. The core remains, shining with clarity, while the atmosphere disperses into beauty. The image is one of serenity, not of struggle. The star has reached the end of its active burning, but it does so gracefully, leaving behind both light and the materials for future growth. When we look at photographs of planetary nebulae taken by space telescopes, we see intricate patterns of color and form. But in the meditative view, what we are seeing is a star completing its rhythm. It is not failure, but completion, not chaos, but transformation. The universe, through these glowing shells, shows that even in endings there can be beauty, even in fading there can be light. For our own sun, this will be its fate. Billions of years from now, after it has passed through its red giant phase, it will shed its outer layers and form a planetary nebula. The Earth may no longer exist in any familiar form by then, but the sun's final act will enrich the galaxy with new material, ensuring that its elements will not vanish, but continue their journey in new stars and worlds. To know this is to see the sun not only as a source of present light, but as part of a larger cycle of creation. And so, planetary nebulae, though brief on cosmic timescales, are among the most meaningful sights in astronomy. They reveal that stars do not simply disappear. They give back to the universe, exhaling their substance into space, where it becomes the seedbed of future light. Each nebula is a whisper of continuity, a reminder that the cosmos is not wasteful, but endlessly renewing. In the night sky, these faint shapes are visible only through telescopes, but their message is clear. The life of stars, even in ending, is part of a larger rhythm. Stars live, shine, expand, and finally release, but the matter and energy they carry remain, folded back into the fabric of the galaxy. To reflect on planetary nebulae is to reflect on continuity, on the calm assurance that even as one chapter closes, another quietly begins. When a star like our sun has passed through the long breath of the red giant stage, when it has shed its outer layers in a luminous planetary nebula, what remains is its core. The vast atmosphere has drifted away, glowing for a while, before dissolving into space. But the central remnant does not disappear. Instead, it becomes something small, dense, and enduring, a white dwarf. A white dwarf is the quiet leftover of a star, a core stripped of fuel and layers, exposed to the universe. It is no longer sustaining fusion, no longer creating energy in its heart. Instead, it glows with the residual heat of its past, like an ember cooling in the night. Though small in size, roughly comparable to Earth, it contains mass close to that of the sun. This density defies imagination. A single teaspoon of white dwarf material would weigh tons on Earth. Yet despite this unimaginable compression, a white dwarf is stable. The stability comes from a form of pressure, different from the one that held the star during its main sequence. With fusion gone, outward thermal pressure disappears. Gravity would try to crush the remnant further, but here quantum physics steps in. Electrons, the tiny particles orbiting atomic nuclei, resist being squeezed into the same state. This resistance, called electron degeneracy pressure, balances gravity. It is not the pressure of heat, but the quiet, fundamental rule of matter that no two electrons can occupy the same place. Because of this, the white dwarf endures, small and compact, yet secure. The light of a white dwarf comes only from its heat. When first formed, it may be extremely hot, with surface temperatures of over 100,000 degrees. It shines brilliantly in ultraviolet and visible light. But there is no new energy being created. Over time, the heat slowly radiates away. The white dwarf cools, glowing more faintly as ages pass. Billions of years may go by before it becomes dark, a hypothetical black dwarf. Yet the universe itself is not old enough for black dwarfs to exist. All the white dwarfs that have formed are still glowing, however faintly. For astronomers, white dwarfs are silent witnesses to the long history of stars. They are found in abundance, scattered across the galaxy, remnants of countless stars that once shone like the sun. Each one is a record of a life completed. Clusters of stars often contain many white dwarfs, showing that even within one group, different stars finish their journeys at different times. One of the most famous white dwarfs is Sirius B, the companion to Sirius, the brightest star in Earth's sky. Invisible to the naked eye, Sirius B was discovered through its gravitational influence on its larger partner. Observations confirmed it as a small but massive object, the first white dwarf ever identified. Since then, thousands have been catalogued, each one a quiet reminder of stellar mortality. The structure of a white dwarf is simple yet profound. Its outer layers are composed mainly of carbon and oxygen, the ashes of helium fusion. Some may have thin shells of helium or hydrogen, but the heart is dense carbon and oxygen, packed tightly under immense gravity. Unlike living stars, white dwarfs do not generate heavy elements through fusion. Their role is to persist, to cool, to fade gradually, marking the final, stable state of small and medium stars. Despite their faintness, white dwarfs influence the galaxy. Their gradual release of heat contributes to the background glow of starlight. In binary systems, where a white dwarf orbits with another star, interactions can occur. If the white dwarf accretes material from its companion, fusion may reignite on its surface, leading to a nova, a temporary brightening. In some cases, too much material can cause the white dwarf to collapse in a thermonuclear explosion, a type Ia supernova. But left alone, a solitary white dwarf is quiet, unchanging, and patient. The timescale of their cooling invites reflection. For billions of years, a white dwarf may radiate softly, growing dimmer with each passing eon. Civilizations may rise and fall, galaxies may drift, yet the white dwarf remains, cooling slowly but steadily. Its endurance is not measured in human spans, but in the lifetimes of the cosmos. In this way, white dwarfs embody persistence, the quiet continuation of being, long after activity has ended. From a meditative perspective, the white dwarf stage is like a final rest. The star has expended its fuel, shown its light, expanded, and released its atmosphere. Now it condenses into a small, dense form and simply cools. It is no longer in balance between fusion and gravity, but in a new kind of equilibrium, defined by the quantum rules of matter. There is no rush, no struggle, only the slow passage of time as the remnant fades. For our sun, this is the ultimate. Fate. Billions of years from now, After it has passed through its red giant and planetary nebula stages, it will become a white dwarf. The Earth may no longer orbit it, and the solar system may be transformed beyond recognition, but the sun's remnant will remain, glowing quietly for billions more years. Its light, though faint, will still carry the memory of the star that once nurtured life on our planet. White dwarfs are not dramatic, but their calm presence carries meaning. They show that even in endings, there is continuity. A star does not vanish. It leaves behind a remnant that endures, cooling slowly but persistently. In their silence, white dwarfs remind us of patience, of endurance, of the quiet after activity has ceased. They are the embers of the cosmos, glowing softly in the dark. When you imagine a white dwarf, picture not a dead star, but a quiet survivor. Its story is not one of sudden disappearance, but of gradual fading, measured across timescales so vast they are almost beyond comprehension. In their stillness, white dwarfs give the galaxy its background of persistence, the soft glow of remnants, the assurance that nothing is truly lost. And so, the white dwarf is the last stage for stars like our sun, not a blaze, not a collapse, but a gentle reduction to essence. Small, dense, patient, and enduring, it shines faintly as time stretches onward. To look at the night sky is to know that many of those faint points are such remnants, ancient stars completing their cycle. They remind us that even the quietest stages of existence are part of the universe's rhythm, and that persistence itself is a form of light. Not all stars share the same quiet longevity as the sun or the countless red dwarfs that fill the galaxy. Some are born with far greater mass, gathering tens of times more matter during their formation. From the very beginning, these massive stars are set upon a different path. They shine more brightly, earn more intensely, and move through their lives much more quickly. Where a small star may endure for billions or even trillions of years, a massive star may live only a few million. Yet in their short lives, they shape the cosmos profoundly, creating elements, sculpting their surroundings, and preparing the way for future generations of stars and worlds. The key to this difference lies in the balance of forces that defines all stars. In a massive star, gravity presses inward with extraordinary strength. To resist collapse, the core must generate immense outward pressure, which means fusion must proceed at a furious pace. The temperatures in the cores of these stars are far higher than those in smaller ones, reaching hundreds of millions of degrees. At such temperatures, hydrogen burns rapidly, converted into helium in vast quantities every second. The light produced shines with brilliant blue-white intensity, visible across great distances in the galaxy. Because fusion in these stars is so fast, the reserves of hydrogen are consumed quickly. A star with 50 times the mass of the sun might last only a few million years before exhausting its core hydrogen. Compared to the quiet endurance of a red dwarf, this is fleeting. Yet during that time, massive stars play an outsized role in shaping the galaxy. Their intense radiation floods surrounding space, pushing away gas, carving cavities in nebulae, and triggering the formation of new stars in neighboring regions. Their stellar winds, streams of charged particles, carry energy and momentum outward, stirring the interstellar medium. When hydrogen in the core is exhausted, a massive star does not stop. The enormous gravity compresses the core further, raising the temperature high enough for helium to fuse into carbon and oxygen. When helium is spent, the cycle continues, with heavier elements forming in sequence neon, magnesium, silicon, and eventually iron. This layered fusion process, unique to massive stars, resembles the rings of an onion, with each shell fusing. a different element. In smaller stars, fusion never progresses beyond helium, but in massive ones, the process advances swiftly through the periodic table. Iron, however, marks a boundary. Fusion of lighter elements releases energy, but iron does not. When the core fills with iron, the process can no longer produce outward pressure. Gravity, relentless as ever, takes over. The result is collapse, rapid and unstoppable. But that belongs to the later chapters of their story. For now, what matters is the recognition that massive stars live with intensity, moving through stages of fusion that smaller stars never reach. The differences in mass also create differences in appearance. Massive stars are often blue or blue-white in color, their surfaces reaching tens of thousands of degrees. They shine thousands or even millions of times more brightly than the sun. They are rare only. A small fraction of stars are born with such mass, but their luminosity makes them disproportionately visible in the night sky. When you see Orion's belt or the bright star Rigel, you are looking at massive stars, brief but dazzling beacons. Despite their brilliance, massive stars are not chaotic. They too rest in balance, with gravity and fusion locked in equilibrium. The balance simply operates at a higher tempo, with greater energy, faster fusion, and shorter timescales. Their lives are not less complete for being brief. They are simply tuned to a different rhythm. The universe, through mass, sets the pace for each star, allowing some to linger softly and others to shine intensely before transforming. The importance of massive stars extends beyond their own lifespans. Through their rapid fusion, they create many of the heavier elements that small stars cannot. Carbon, oxygen, and silicon, all vital for planets and life, are produced in their cores. When these stars reach their end, they release these elements into space, enriching the galaxy. Without massive stars, the universe would remain simple, composed mainly of hydrogen and helium. It is through their short but productive lives that complexity arises, and with it, the possibility of life. In this way, massive stars embody a paradox. Though they are rare and short-lived, they are central to the ongoing story of the cosmos. Their energy sculpts galaxies, their fusion creates elements, their endings distribute those elements into space. Small stars endure, providing stability, but massive stars transform, providing richness. Both are needed, and both arise naturally from the same process of star formation, determined by the amount of matter gathered at birth. From a calm perspective, this diversity can be seen as part of the universe's harmony. There is no single ideal path for a star. Some move slowly, others quickly. Some shine faintly for eons, others brilliantly for moments. Each contributes to the rhythm of creation. Massive stars, though they live fast, are no less part of the cosmic balance. Their brilliance is simply one expression of what mass makes possible. When you look up at the brightest stars in the night sky, many of them are massive. Their light has traveled hundreds of thousands of years to reach you, but the stars themselves may not live for much longer on cosmic scales. Yet in their brief lives, they provide some of the most striking sights in the heavens, markers of the galaxy's living energy. Their brilliance is not tragedy but gift, a way the universe shares its variety. In time, these stars will move beyond the stages we have described, collapsing and exploding, leaving neutron stars or black holes. But even before that, in their main sequence and giant stages, they are already shaping their surroundings, already preparing the future. To reflect on massive stars is to reflect on the intensity of life, the way different rhythms coexist in the same universe. Their endings may be different, but their presence is essential. And so, massive stars follow a different ending. not because they choose, but because mass determines their path. Their gravity drives fusion to extremes. Their pace is swift, their lifespans short. Yet in that short span, they give more than their share to the cosmos. They create elements, sculpt space, and remind us that brilliance and brevity can exist together. In the quiet of the night sky, their blue-white glow tells us that the universe values variety, that even fleeting stars have a lasting role in the balance of creation. When a star is born with enormous mass, greater than 10 or 20 times that of the Sun, its destiny is set on a path of intensity and transformation. These rare giants of the cosmos shine with dazzling brightness, outshining thousands of ordinary stars. Yet beneath their glow lies an interior more complex than anything found in smaller suns. As they age, massive stars become supergiants, swollen in size, blazing in power, and layered within like the rings of a tree. Each layer represents a stage of fusion, a shell where elements are quietly transformed into heavier ones, step by step, in the great rhythm of stellar life. The beginning is the same as in all stars. Hydrogen fuses into helium in the core. But in supergiants, the pace is swift, driven by the immense gravity pressing inward. Their hydrogen is consumed quickly, sometimes in only a few million years. Once this first stage ends, the core contracts and heats further, allowing helium to fuse into carbon and oxygen. In smaller stars, fusion might stop here. But in supergiants, gravity's relentless pressure drives the process onward. When helium runs low, new shells ignite, each burning a heavier element than the one before. The result is a star with multiple shells of fusion stacked around the core. At the very center, iron begins to accumulate, the endpoint of fusions. Energy-giving reactions. Surrounding this iron core is a shell where silicon fuses. Above that oxygen, then neon, then carbon, then helium, and finally hydrogen at the outer edge. Each shell burns at its own pace, with the inner layers operating at ferocious speeds, while the outer layers proceed more gently. Together, they form a structure of remarkable order, a cosmic onion of fire. From the outside, a supergiant may appear steady, glowing red or blue, depending on its surface temperature. Red supergiants, like Betelgeuse and Orion, are enormous. Their atmospheres stretch so far that if placed in our solar system, they would engulf the orbit of Jupiter. Supergiants, hotter and more compact, radiate with piercing brilliance. Both are manifestations of the same underlying process: immense mass driving fusion through successive stages, building layer upon layer within. The timescales of these layers differ dramatically. Hydrogen burning in the core may last millions of years. Helium burning, only hundreds of thousands. By the time the star is fusing silicon into iron, the process may take mere days. This acceleration reflects the increasing demand of gravity and the decreasing energy yield of each fusion step. The deeper the star moves into heavy elements, the faster it must burn them to resist collapse. The structure becomes not only layered, but dynamic, with inner shells flickering on and off, igniting and extinguishing in rapid succession. Despite this complexity, the principle of balance still holds. Gravity pulls inward, fusion pushes outward, and the star finds equilibrium at each stage. What makes supergiants remarkable is how many times this balance must be re-established, how many layers are stacked in harmony. The star does not fall into chaos. Instead, creates order, arranging its interior into a nested series of shells, each one burning quietly, contributing to the whole. For astronomers, supergiants are laboratories of element formation. Within their depths, nearly all the naturally Occurring elements up to iron are created. Carbon, nitrogen, oxygen, silicon, and more all are forged in these layered furnaces. The star is not just shining. It is building the material that will one day seed planets and life. Without supergiants, the periodic table would remain sparse, and the cosmos would lack much of its richness. Their layers within layers are this universe's way of preparing for diversity. Observing supergiants from Earth, we see not their inner structure, but their outer signs. Their size, brightness, and variability hint at the processes within. Some pulsate gently, their surfaces expanding and contracting in rhythm, as the balance of energy shifts between layers. Others shed mass through strong stellar winds, carrying away material that will later enrich space. Even in their appearance, they reveal the complexity of their inner lives, translated into patterns of light and motion. Betelgeuse is one of the most studied supergiants, partly because it is close, enough for astronomers to resolve details of its surface. Its reddish hue and irregular brightness reflect the turbulent convection of its vast atmosphere. Inside, it is layered with shells of fusion, steadily building toward the final stages of its life. Though it may appear calm to the naked eye, its interior is a tapestry of nested processes, each one essential to the star's balance. The life of a supergiant reminds us that complexity can be harmonious. Dozens of processes, earning at different rates, operating in different regions, coexist without disorder. The star holds them all together under the steady pull of gravity. Its immense energy is not wasted, but organized into a sequence of transformations, each preparing for the next. This is why astronomers often speak of stellar evolution not as chaos, but as a progression, a rhythm of change that follows natural rules in time. The iron core at the center of a supergiant will grow too heavy. Fusion can go no further, for iron does not release energy when combined. At that moment, the delicate balance finally fails and collapse begins, leading to the dramatic end of a supernova. But before that final act, the star spends thousands to millions of years as a layered giant, holding together its complex interior with grace. The quiet before the transformation is itself a remarkable stage, a testament to the resilience of balance. From a reflective point of view, supergiants embody the idea of depth. What we see on their surfaces is only a fraction of the story. Beneath lies a structure more intricate than any planet or world, a nested system of layers, each glowing with its own fire. They are not chaotic, but profoundly ordered, showing how even the most massive and intense stars find equilibrium in complexity. And so, supergiants remind us that the universe contains not only endurance and simplicity, but also intricacy. They are the architects of the elements, the cosmic forges where matter is transformed stage by stage. To look at a supergiant is to glimpse a layered story, written not in words, but in shells of fusion, each one part of the whole. Their lives may be short, but their depth leaves an enduring legacy, carried forward in the atoms of everything that follows. Every star follows its path according to the mass it was given at birth. For the most massive, the journey does not end quietly, as it does for stars like our Sun. Instead, after living briefly but intensely, after passing through the layered complexity of the supergiant stage, these stars reach a final moment when balance can no longer be maintained. This stage is called a supernova. The word itself often suggests drama, but in truth, it is simply another transition, a final step in the rhythm of stellar life. To approach it calmly is to see not catastrophe, but transformation. At the heart of a massive star, fusion proceeds, layer by layer, building heavier elements with each stage. Hydrogen becomes helium. Helium becomes carbon and oxygen. Then neon, magnesium, silicon, and eventually iron. Each step releases energy, supporting the star against gravity. But when the core is made mostly of iron, the process reaches a boundary. Iron does not yield energy when fused. It absorbs energy instead. No further equilibrium can be found. Gravity, always patient and steady, begins to compress the core beyond what fusion can resist. As the iron core contracts, temperatures and pressures rise to extraordinary levels. The outer shells, still burning in their own layers, pour energy into the center. But now the balance collapses inward. The core becomes so dense that protons and electrons combine into neutrons, releasing a flood of neutrinos, lightweight particles that stream outward at nearly the speed of light. Within seconds, the core shrinks from a size similar to Earth to something no larger than a city. In that collapse, the story of the star changes forever. What follows is the outward response to that inward contraction. The outer layers, suddenly unsupported, fall inward as well. When they strike the dense core, the infalling matter rebounds, sending shock waves through the star. These shock waves, energized by neutrinos and the release of gravitational energy, push the outer layers outward with immense force. The star's atmosphere is expelled into space, carrying with it the elements forged during its life. For an instant in cosmic time, the star brightens enormously, shining as much as billions of ordinary stars. This is the supernova. Yet, the physical process is powerful. Its meaning is gentle. A supernova is not simply destruction. It is creation on a grand scale. The outer layers carry into space the carbon, oxygen, silicon, and iron formed in the star's fusion cycles. In the explosion itself, even heavier elements are created: gold, uranium, iodine, and many others. These atoms, scattered across the galaxy, become part of new stars, planets, and eventually living organisms. Without supernova, the universe would lack much of its richness. The calcium in bones, the iron in blood, the gold in jewelry, all trace back to stars that ended this way. Astronomers observe supernova both in distant galaxies and more rarely in our own. In 1987, a supernova was observed in the Large Magellanic Cloud, a nearby galaxy. It provided one of the clearest views of the process, including the detection of neutrinos that confirmed the theory of core collapse. In our own Milky Way, remnants of past supernova can be seen in glowing clouds of gas, such as the Crab Nebula. These remnants are not violent scars, but luminous structures, expanding quietly through space, their filaments shining with the light of released energy. The star, left behind, also changes form. If the remaining core is small enough, it stabilizes as a neutron star, an object so dense that a spoonful would weigh billions of tons. If the core is larger, it may collapse further into a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. These remnants, though extreme, are simply the natural outcomes of mass and gravity. They are not monsters, but part of the cycle, continuing the story in new forms. From a reflective perspective, a supernova can be seen as the universe's way of renewal. Just as planetary nebulae return the matter of smaller stars to space, supernova return the enriched matter of massive ones. The difference lies in scale. Where a planetary nebula glows softly for tens of thousands of years, a supernova briefly illuminates entire galaxies. Both, however, serve the same purpose: to recycle matter, to feed the cosmos with material for future generations. It is easy to imagine the word explosion as violent. But if we step back to the time scale of the universe, a supernova is but a momentary breath. The star, having lived briefly, exhales with intensity, scattering its substance into the galaxy. That scattering is not chaos, but contribution. Out of the release comes the building material of worlds. Out of the end comes a beginning. To think of it this way is to soften the edges of the event, to see it not as destruction, but as balance restored in a new form in the night sky. When astronomers detect a supernova, it is often visible only for weeks or months before fading. But the remnant lingers, expanding into a nebula that may last for tens of thousands of years. Over time, those remnants mix with interstellar clouds, enriching them. From those clouds, new stars will form, beginning the cycle again. Thus, every supernova is part of the ongoing rhythm. Earth, life, transformation, renewal. For humanity, the significance of supernova extends inward. Our bodies carry atoms made in such stars. Every breath of oxygen, every molecule of calcium, every trace of iron came from stellar furnaces and stellar deaths. To reflect on this is to feel connected, not just to the stars that shine today, but to the stars that ended long before Earth formed. Their final transformations became the foundation of our existence. And so, a supernova is not simply a grand event in astronomy, but a quiet truth about continuity. Massive stars live differently from smaller ones, and they end differently, too. Their final act may brighten galaxies for a time, but its deeper gift is the distribution of elements, the enrichment of the cosmos, the preparation for future stars and worlds. In this way, even endings become beginnings, and even the brightest transformations are part of the calm rhythm of the universe. When a massive star reaches the end of its journey and undergoes the transformation of a supernova, much of its outer material is expelled into space, enriching the galaxy with new elements. But the very core of the star does not disappear. Instead, it is compressed to a state unlike anything else we know. If the mass of the core is too great to become a white dwarf, but not quite large enough to collapse into a black hole, it becomes a neutron star. These objects are among the most extraordinary in the universe, dense beyond imagination. Small in size, but immense in weight, quiet in their endurance, yet remarkable in their nature. A neutron star begins when gravity, unchecked by fusion, crushes the core of a massive star. Protons and electrons, normally separate, are forced so tightly together that they combine to form neutrons. In this way, matter becomes a sea of neutrons packed together, held stable by the rules of quantum physics. What results is a body only, about 20 kilometers across, roughly the size of a city, but containing more mass than the sun dot. To imagine the density of a neutron star is to stretch the limits of human thought. A teaspoon of neutron star material would weigh billions of tons on Earth. It is not ordinary solid matter, but an exotic state where neutrons themselves are pressed shoulder to shoulder. The pressure resisting gravity in this case is called neutron degeneracy pressure, a fundamental rule that neutrons, like electrons, cannot occupy the same state. This pressure halts collapse, leaving the star stable as a neutron star. Despite their extraordinary properties, neutron stars are often invisible to the human eye. They are so small that their light is faint. Many cool over time, emitting primarily in X-rays or radio waves rather than visible light. Yet they are far from absent. Across the galaxy, neutron stars number in the hundreds of millions, silent reminders of the countless massive stars that have ended before. Some neutron stars reveal themselves through regular pulses of radiation. These are called pulsars. As a neutron star spins, beams of radio or X-ray light sweep outward from its magnetic poles. If one of these beams passes across Earth, we observe it as a pulse, repeating with remarkable regularity. Some pulsars rotate many times per second, faster than a kitchen blender, yet they remain steady for millions of years. Their rhythm is so precise that astronomers once compared them to cosmic clocks. In this way, even in their silence, neutron stars offer a steady signal of order in the cosmos. Not all neutron stars spin rapidly. Some rotate more slowly, while others slow down over time. But whether pulsing or quiet, they share the same essence: immense density, tiny size, and stability after transformation. For those formed in binary systems, where a neutron star orbits with another star, new interactions can occur. Matter may fall from the companion onto the neutron star, creating bursts of energy detectable across space. Yet even these outbursts are simply part of the rhythm of stellar evolution, another way that remnants continue to shape the universe. From Earth, we cannot see neutron stars directly with our eyes, but telescopes detect their signatures in radio waves, X-rays, and even gravitational waves when two collide. Observations of these collisions have confirmed that neutron stars are key sites for the creation of heavy elements such as gold and platinum. Just as supernovae enrich space with elements, so too do neutron star mergers. The cosmos uses even these dense remnants as forges, turning their immense energies into the building blocks of worlds. The lifespan of a neutron star is immense. Once formed, it cools slowly, radiating away its heat over billions of years. Like white dwarfs, neutron stars are stable endpoints, not prone to sudden change. Their persistence across cosmic time means that they remain as quiet markers of stellar life cycles. Each neutron star in the galaxy is a survivor, an object that has endured the extremes of gravity and compression, now resting in a steady state. Though they are exotic, neutron stars remind us of continuity. They form from stars that lived, shone, and died, and they themselves may one day give rise to new stories, as their matter is recycled through collisions or eventual decay. They are not final in the sense of disappearance, but part of an unbroken chain. The universe does not waste them, just as it does not waste the gases of planetary nebulae or the elements of supernovae. All is folded back into the rhythm of creation. From a meditative perspective, neutron stars are symbols of concentration. All the mass and energy of a star is gathered into a tiny sphere, condensed into a quiet form that still radiates across time. They are compact, enduring, and silent, like embers hidden beneath ash, glowing softly long after the fire has passed. Their presence in the galaxy is not obvious, but it is constant, a background of persistence that underlies the brilliance of brighter stars. If you allow yourself to reflect on them, neutron stars reveal something about balance at extremes. They are neither collapsing endlessly into black holes, nor expanding into diffuse gas. They rest at a boundary, where quantum rules halt gravity, where density finds stability. They embody the principle that even in the most intense conditions, the universe finds ways to create harmony. For massive stars, becoming a neutron star is not failure, but fulfillment of their path. After burning brightly and ending in a supernova, they condense into quiet remnants that continue to shape the cosmos. Their density creates new opportunities for element formation. Their pulses offer steady rhythms, and their collisions seed galaxies with rare elements. They are the silent architects of continuity, their influence subtle but profound. And so, neutron stars are among the quietest yet most remarkable objects in the universe. They are small but immensely heavy, silent but enduring, exotic but natural. outcomes of stellar evolution. To think of them is to appreciate the depth of the cosmos, the way stars live not only in their shining, but in their remnants. Every neutron star is a testimony to persistence, to the quiet strength that remains. After brilliance has faded, they remind us that even in endings, the universe creates stability, and that silence itself can be powerful. When the most massive stars reach the end of their lives, even the extraordinary balance that sustains neutron stars cannot hold. After burning through their fuel, after layering fusion shells deep inside, and after releasing their outer layers, in a supernova, what remains at the core may still be too heavy for stability. In such cases, gravity is not stopped by electron pressure, as in white dwarfs, nor by neutron pressure, as in neutron stars. Instead, gravity continues its steady inward pull, compressing the matter beyond known limits. The result is what we call a black hole. The phrase black hole often evokes images of violence or danger. Yet, when described calmly, a black hole is simply the final, stable state of matter compressed so completely that nothing, not even light, can escape its gravity. It is not chaos, but completion. A black hole is the quiet continuation of gravity's work, carrying a massive star beyond the forms we can easily picture, into a region defined by simplicity rather than complexity. The key feature of a black hole is its event horizon. This is the boundary around it, the surface beyond which nothing can return. Light that crosses this boundary cannot escape, which is why the object appears black. But outside the horizon, space remains unchanged. Planets, stars, and gas can orbit a black hole just as they would orbit any massive body. If the sun were to be replaced by a black hole of the same mass, Earth's orbit would continue unchanged. The difference lies only within the horizon, hidden from view, where gravity compresses matter beyond reach. At the center of a black hole lies what theory describes as a singularity, a point of infinite density where our current understanding of physics cannot fully describe conditions. Whether this singularity is truly a point or something else is unknown. What we do know is that the black hole contains within it all the mass of the collapsed star, held together by gravity alone. Though the concept stretches our comprehension, it is simply the outcome of gravity's persistence when no other force remains strong enough to resist. Black holes come in different sizes. The smallest, known as stellar mass black holes, form from collapsing stars with masses several times greater than the Sun. Larger ones, intermediate and supermassive black holes, are found at the centers of galaxies, including our own Milky Way, while the origins of the largest black holes are still studied. The principle is the same. Gravity gathers matter so densely that an event horizon forms, and a black hole exists. From Earth, we cannot see black holes directly, but we detect their presence through their influence. Gas falling toward a black hole heats and emits X-rays, which telescopes observe. Stars orbiting unseen centers reveal the hidden mass within. In 2019, astronomers captured the first image of a black hole's shadow in the galaxy M87, a glowing ring of light surrounding the darkness of the event horizon. Even in these observations, the black hole is not revealed as a thing of chaos, but as a region of silence surrounded by luminous motion. Black holes, despite their reputation, are part of the cycle of balance. They do not roam the universe devouring everything in sight. Instead, they exist quietly, affecting only what comes too close. Many drift unnoticed, remnants of massive stars that collapsed eons ago. Their presence is subtle, their nature hidden, but their role is important. They represent the final endpoint of gravity's strength, the simplest state that matter can reach when compressed beyond all other forms in binary systems. Where a black hole orbits with a companion star, interactions can produce bright displays. Gas drawn from the companion swirls into an accretion disk, heating and glowing as it falls inward. These systems allow astronomers to study black holes indirectly, measuring their masses and spins. Yet even here, the black hole itself remains quiet, simply shaping space with its gravity. While the light we see comes from matter outside the horizon, black holes also play a role in the grander scale of galaxies. The supermassive black holes at galactic centers, millions or billions of times the sun's mass, anchor their galaxies. Their influence shapes the motion of stars, the flow of gas, and even the formation of new stars. They are not destructive, in essence, but stabilizing, providing gravity's center for vast structures. Without them, galaxies might not hold together as they do. From a reflective view, black holes remind us that endings can be both mysterious and calm. They are not violent devourers, but silent keepers of gravity's deepest truth. They embody the idea that matter, when pressed beyond all resistance, finds rest in a state hidden from light. They remind us that not all things are meant to be seen, yet they still exist as part of the universe's balance. Even the thought of a black hole can be soothing when placed in context. The light we see in the night sky comes from stars burning. Their fuel, planetary nebulae, glow softly with released gases. Supernovae flare briefly with intensity. Black holes, by contrast, are quiet. They shine with no light of their own, make no sound, and reveal themselves only indirectly. In their silence, they show another form of stability gravity at its purest, undisturbed, continuing endlessly. For the most massive stars, this is their fate: to live briefly, to shine with brilliance, to end in collapse, and to rest as black holes. From their beginnings in nebulae to their final state, they follow the same laws that govern all stars, only carried to greater extremes. Their story is not a tragedy but a completion, a journey through all phases of balance until only gravity remains. And so, black holes can be seen not as frightening, but as part of the gentle rhythm of the cosmos. They are the silent outcome of massive stars, the quiet centers around which galaxies turn, the hidden reservoirs of gravity's strength. To reflect on them is to accept that not all truths are visible, and not all presences are luminous. Some exist in silence, shaping the universe in ways we cannot see. In that silence lies calm, endurance, and the quiet continuation of the cosmic cycle. When we look at the night sky, stars often appear solitary, scattered across the darkness like individual lanterns. Yet, in truth, most stars are not born alone. They emerge from vast clouds of gas and dust that give rise not just to one star, but to many at once. These siblings of starlight remain near each other, bound at first by the gravity of their shared birth. Such families of stars are called clusters, and they remind us that even in the immensity of space, companionship is. Common dot star clusters form in stellar nurseries, those dense regions of molecular clouds where gravity pulls matter together. Because the clouds are large, they fragment into many dense knots rather than just one. Each knot collapses into a star, and together they form a cluster. These stars are born at nearly the same time, from the same material, carrying the same chemical fingerprints. In this way, a cluster is a cosmic family, its members linked by origin, even as their individual paths may differ. There are two main kinds of star clusters: open clusters and globular clusters. Open clusters are young, loose gatherings of dozens, hundreds, or sometimes thousands of stars. They are spread out, their stars easily distinguished from one another. The Pleiades, also called the Seven Sisters, is a well-known open cluster. Visible to the naked eye, its bright blue stars sparkling like a small dipper in the sky. Globular clusters, by contrast, are ancient and densely packed, containing hundreds of thousands of stars held together in a spherical shape. They orbit the galaxy as great swarms, relics of its earliest days. Open clusters tell the story of youth. Their stars are hot and bright, often still surrounded by traces of the gas from which they formed. Because the gravitational bonds in open clusters are weak, they gradually disperse. Over time, individual stars drift away, joining the wider population of the galaxy. Yet even as they scatter, their shared chemistry reveals their common past. Astronomers can trace these siblings across space, recognizing the family connections. Hidden in the starlight, globular clusters, on the other hand, tell the story of endurance. They are among the oldest structures in the galaxy, dating back more than 10 billion years. Their stars are old and faint, many of them red giants or white dwarfs, survivors from the galaxy's youth. Packed closely together, they appear as glowing spheres through telescopes, each one a swarm of ancient suns bound tightly by gravity. They orbit the halo of the Milky Way, shining like timeless lanterns around the galactic core. Clusters also provide insight into the life cycles of stars. Because all stars in a cluster form at the same time, astronomers can compare them to see how mass shapes destiny. In a young cluster, massive stars may already be leading the main sequence, while smaller ones remain unchanged. In older clusters, only the faintest stars remain on the main sequence, the brighter ones having evolved into giants or remnants. By studying clusters, we learn not just about individual stars, but about the shared rhythms of stellar evolution. From a meditative perspective, clusters remind us of togetherness. Stars that seem solitary in the night sky often begin in community. Their light is not just individual, but collective, born from the same cloud, traveling outward side by side. Even when clusters eventually disperse, the memory of that shared beginning lingers in their chemistry and their trajectories. The universe shows us, through clusters, that companionship is part of its design. The presence of clusters also shapes galaxies. Open clusters provide young stars that eventually spread into the galactic disk, replenishing its population. Globular clusters act as tracers of galactic history, marking the shape of the halo and recording the conditions of the early universe. Together, they reveal both the youth and the age of galaxies, showing that star formation is not a solitary act, but a collective one, woven into the galaxy's structure. Some clusters contain stars so close together that their mutual interactions shape their evolution. Binary systems, triples, and higher multiples are common, forged in the density of cluster environments. These close companions influence each other's lifespans, exchanging material or altering their paths. Even in these crowded conditions, balance is found, with gravity weaving connections that endure across time. When we observe the Pleiades, the Hyades, Omega Centauri, or M13 in Hercules, we see not just stars, but families. Each cluster is a portrait of stars together, sharing an origin, moving in harmony for a time before dispersing. They remind us that stars, like people, often begin in company, even if their later journeys carry them apart. For the sun, the story is no different. It too was likely born in a cluster billions of years ago, with siblings that have since wandered across the galaxy. We do not know exactly where those siblings are today, but astronomers have identified stars with similar chemical signatures that may once have shared the sun's birthplace. To reflect on this is to realize that even our star began in togetherness, part of a larger group that has now dissolved into the background of the Milky Way. And so, star clusters are gentle reminders of community in the cosmos. They are the gatherings where stars are born, the nurseries where companionship shapes the beginning of stellar life. Open clusters speak of youth and dispersal, globular clusters of age and endurance. Together they tell us that stars are not simply points of light, but members of vast families, connected across space and time out in the night sky. When you see a cluster with your eyes, or through a telescope, you are seeing not just stars, but relationship stars. Born together, shining together, bound for a time before drifting apart. To rest with this thought is to feel the quiet truth that even in the vastness of the universe, there is companionship, harmony, and shared origin. From the beginning of the universe, matter has been in motion, shifting and transforming through cycles of creation and renewal. The earliest cosmos was simple. Hydrogen, helium, and faint traces of lithium filled space after the first expansion. Everything else, the oxygen we breathe, the calcium in our bones, the iron in our blood, had yet to appear. These elements were made later in the hearts of stars. The story of stars is therefore not only about light, but also about matter, the gradual enrichment of the universe with the ingredients for complexity and life. Inside stars, fusion turns simple elements into heavier ones. In small stars, hydrogen fuses into helium, slowly and steadily. In more massive stars, helium fuses into carbon and oxygen, and into heavier elements like neon, magnesium, and silicon. In the largest stars, even iron is formed, though fusion stops there. Beyond iron, elements emerge only in the extraordinary conditions of supernova or neutron star collisions, where immense energies forge gold, uranium, and other rare atoms. This gradual layering of creation builds the periodic table, one element at a time, across billions of years. But creation inside a star is only part of the cycle. For those elements to shape planets or life, they must be released into space. Small and medium stars do this gently, exhaling their atmospheres into planetary nebulae and leaving white dwarfs behind. Massive stars release their elements in more dramatic fashion, through supernova or stellar winds, spreading enriched matter across their surroundings. Neutron star mergers add further richness, scattering heavy elements into the galaxy. Each stage of stellar life contributes, ensuring that matter is not locked away, but shared. The gas and dust released by stars drift into interstellar clouds, mixing with hydrogen and helium already present. Over millions of years, these clouds condense into new stars and planets. Thus the cycle continues. Stars are born, they shine and fuse, they release their elements, and from that enriched material new generations arise. The universe is therefore a vast recycling system, where matter is never wasted, but constantly reshaped. For Earth, this cycle is personal. Every atom heavier than hydrogen or helium in our bodies was formed in a star. The carbon in living cells, the oxygen in lungs, the nitrogen in proteins, the phosphorus in DNA, all were created in stellar cores or supernova. Even the iron that allows blood to carry oxygen was forged in the death throes of massive stars. To reflect on this is to recognize that life is not separate from the cosmos, but deeply rooted in it. We are, in the most literal sense, made of star matter. Planets, too, bear the signature of stellar creation. The rocks beneath our feet contain silicon and magnesium born in earlier generations of stars. The oceans hold oxygen and hydrogen, one ancient, one created later. The air carries nitrogen and carbon, balanced by life, but supplied by the stars. When we drink water, breathe air, or hold stone, we interact with the legacy of countless stellar cycles. The world around us is a record of billions of years of fusion and release. This awareness reshapes how we see the night sky. Stars are not distant, unrelated lights, but kin. Their life cycles feed directly into ours. Without their creation of elements, Earth could not exist, and life could not have emerged. When we look up at the stars, we are looking at the forges that shaped our own chemistry, the ancestors of our atoms. The phrase, "we are stardust," is not poetry alone, but a quiet scientific truth, one that carries profound calm. The cycle of elements also shows us continuity. Nothing is lost. The gas released by one generation becomes the seed of the next. The elements forged in ancient stars billions of years ago still persist, now part of mountains, oceans, forests, and people. Even as stars die, their essence remains, woven into new forms. The universe's rhythm is not one of endings but of renewal, where each transformation creates the possibility of something else. Astronomers study the chemical makeup of stars to trace this history. By analyzing the light of a star, they can see which elements it contains, and therefore how many generations of stellar enrichment preceded it. Younger stars, like the Sun, are rich in heavy elements because they formed from material recycled many times. Older stars, born early in the galaxy's life, contain only small traces of heavier atoms. In this way, the stars carry records of the universe's memory, written not in words, but in light and chemistry. From a calm perspective, the cycle of elements offers reassurance. Just as stars recycle matter endlessly, so too does life recycle on Earth. Plants take in carbon dioxide and release oxygen. Animals breathe in oxygen and return carbon. Oceans circulate water. Soils renew themselves. The patterns we see around us echo the patterns of the stars. On every scale, from the smallest cell to the galaxy itself, continuity emerges. The next time you see a star, you may imagine the quiet transformations happening within it. Hydrogen becoming helium, helium becoming carbon and oxygen, layers of fusion building gradually. You may also imagine the gentle release of those elements in time, drifting into space, settling into new clouds, beginning again. From this perspective, starlight becomes not only light, but a promise that matter itself is always part of a greater cycle, moving from one form to another, endlessly. And so, the cycle of elements links stars to life. Stars create, stars release, and stars renew the universe with their gifts. Planets, air, water, and living beings are part of this chain. To recognize this is to feel connected not only to Earth, but to the galaxy, not only to our own time, but to billions of years of cosmic history. The rhythm of the stars is also the rhythm of life, calm, continuous, and unbroken. When we look into the night sky, the stars appear timeless, scattered across the darkness as though fixed in place. Yet every one of those lights is part of a cycle, a process that stretches across billions of years. Stars are born, they shine, they transform, and eventually they fade or collapse. From their remnants, new stars are formed, continuing the sequence. This is the cosmic rhythm, the endless pattern of birth and death that defines the life of the universe. It is not chaos, but continuity, not destruction, but renewal. The beginning of the rhythm lies in clouds of gas and dust. Within these vast regions, gravity slowly gathers matter into dense knots. Protostars take shape, warming as they contract, until nuclear fusion ignites and they join the main sequence. For millions or billions of years, they shine steadily, balancing gravity and energy. Then, As fuel runs low, the balance shifts. Stars swell into giants, shed layers, or collapse. Some end gently as white dwarfs, others more intensely as neutron stars or black holes. Each ending scatters matter into space, enriching it with new elements. From those enriched clouds, new stars are born. The cycle begins again. What makes this rhythm remarkable is its patience. Each step unfolds over timescales far beyond human experience. A star like the Sun spends billions of years in stability before changing. Even the briefest stars live for millions of years. The rhythm is slow, steady, and unhurried. Nothing is wasted, nothing rushed. The universe keeps its pace with quiet assurance, allowing matter to move from one form to another in seamless continuity. The death of one generation becomes the birth of the next. Gas expelled by planetary nebulae or blasted outward by supernova mixes with interstellar clouds. Within those clouds, new protostars gather. In this way, the atoms that once belonged to old stars become the building blocks of new ones. Planets form from the leftover material in disks, carrying within them the same elements forged in stellar cores. Life itself arises from this recycled matter. Every breath of oxygen, every molecule of carbon, every trace of iron in blood carries the memory of stars that lived and ended long ago. That to think of the cosmic rhythm in this way is to see the universe as a vast, interconnected cycle. Stars are not isolated events, but part of a flow. Birth and death are not opposites, but stages of the same process. What seems like an ending is only a transformation, matter reshaped into new beginnings. The rhythm is not fragile, but enduring, repeating endlessly across galaxies, filling the cosmos with light and structure. The rhythm also carries variety. Some stars move slowly, lasting for trillions of years. Others burn quickly and end in brilliance. Some become faint white dwarfs, others dense neutron stars, others silent black holes. Each path is different, yet all are woven into the same cycle. The diversity enriches the whole, ensuring that the universe contains both longevity and change, stability and transformation. From Earth, the night sky reveals this rhythm in glimpses. Nebulae show the birthplaces of stars. Clusters reveal stars in different stages of life. Supernova remnants glow as reminders of endings that are also beginnings. The galaxy itself, with its spiral arms filled with young stars and its halo of ancient clusters, is a portrait of the cycle on the grandest scale. Even the faint background of starlight that fills the night is part of this rhythm, the combined glow of countless generations of stars. The cosmic rhythm has no final destination. Stars will continue to be born as long as gas remains in galaxies. Their light will continue to shine, their elements will continue to circulate. Even as galaxies evolve, merge, or change, the pattern of birth and death persists. On timescales so vast, they are almost unimaginable. The rhythm may shift, but its essence remains. Creation and renewal are written into the fabric of the cosmos itself. From a reflective perspective, this rhythm carries comfort. It shows that the universe does not waste, does not stop, but continues to transform. Every star, no matter how small or great, contributes to the whole. Its birth adds light, its life sustains balance, its death enriches space. Nothing is lost. Everything is folded back into the cycle. To see this is to feel continuity, to sense that the cosmos moves with harmony, and that even endings are gentle. Transitions within an eternal flow. For us, the rhythm is deeply personal. Our bodies carry atoms forged in stars. Our planet formed from their remnants. our light and warmth come from one still shining. We are part of the cycle, not separate from it. The rhythm of stars is also the rhythm of our own existence, connecting us across time and space. To breathe, to live, to look at the sky, is to participate in the same continuity that has shaped the cosmos for billions of years. And so, the cosmic rhythm of endless birth and death is not a story of loss, but of persistence. It is the quiet heartbeat of the universe, slow and steady, sustaining galaxies and life alike. To reflect on it is to feel calm assurance that the stars we see are part of an unbroken chain, that their light is both ancient and renewing, and that the universe itself is a cycle of continuity. Birth flows into death, and death into birth, endlessly, softly, without haste. This was the Sleepy BrainDose. Thank you for letting these quiet stories of stars keep you company. May their calm rhythm stay with you, like a steady breath, guiding you into rest. Good night, and let the universe hold you softly.